Welcome back. In the last video, we cover multiple linear regression with the stats model. In this video, we're going to go into feature extraction as well as trying to locate features that is important, as well as identifying features that's not important for the purpose of our modeling. So in the first tool that we use is the correlation coefficient. It is a really useful tool to identify collinearity between predictors. So let's just run this. So what I did do is I just set my pandas display float format to 4 decimals only, and we store the correlation matrix into the variable called core_matrix. So when you actually run this, couple of things. It's a little bit clouded for our eyes to be able to actually pick up all the details. So what I've done here is that I have intentionally masked those with correlation matrix that's less than 0.6, sorry. If it's less than 0.6, I set it to 0. With the intent of only highlighting those with greater than 0.6 correlation coefficient. Again, this is not so easy, but it's better than before. So you have 0.72 here, 0.62 here, 0.66 here, and also a minus 0.76 here. So that's really what I'm looking out for. Of course, I did show you guys in the last video that we can use heat map to actually help us to visualize. Again, what we did plotting here is the core matrix, which is this one here. Now the color is a little bit undesirable, but that's okay. It actually does what we want it to do. All the zero are set to the color teal, and you can see the blue. Now I don't know what you call this color, light brown. You can see the 0.6, 0.72. These are all the so-called variables with very high correlation with other variables. So indus, for example, is highly correlated to LSTAT, and tax negatively correlated to distance, highly correlated to age, as well as the pollution index or the nitric oxide. Okay, so this is one way to actually do that using the correlation matrix. From here, you can also see another 1.91 here, which is really high between tax as well as RAD. Okay, so detecting collinearity, there's another way to do it is using eigenvector. We use the NumPy's linear algebra eigen decomposition of the correlation matrix, and we just plot that out and let you see in terms of those with so-called significance. Now 8, 10, and 11 here is near to 0 or very small compared to others. So this is the eigenvalues. You can see that this eigenvalue is really small. Now the small value like this basically represent that there's a presence of collinearity in this specific index here. So we dig into the actual eigenvectors decomposition. This is the eigenvalues. We are looking at the eigenvectors itself, and we run this and looking at specifically and sorting it out. Basically, look at those with very high loading compared with the rest. From here, we can see that index 2, 8, and 9 are those with the highest loading, meaning they contribute the most to this low value of number 8 eigenvalues. So we print out the names of these as indus, RAD, as well as tax. Just to refresh your memory of what indus, RAD, and tax are, so come back here looking at the description. Indus is basically proportion of non-retail business acres per town. RAD is index of accessibility to the highways, and also tax is full value of property tax rate per $10,000. And we can see that these are the factors that are causing the multi-collinearity problem in essence. Now, just to revisit the feature importance as well as the extraction, a couple of things from the so-called coefficient that we have generated. Let me just get to this page here. From the coefficient, there are a couple of things that you can observe. One is the direction. This is 36. Of course, that's the intercept. Nox here is minus 17, which is rather large, and the highest positive value is Rm at 3.8. Okay, so you can tell from the couple of things you do need to check, one is the direction of the coefficient, which we just did. Second one is the impact of the variable or the factor on the overall model here. Yes, the direction of the coefficient is important, but how significant is it to the overall scheme of things or the model itself? There are two ways to do this. The first one is that we standardize the variable to identify key features. Now understand that the distribution of the actual so-called features itself are quite different. Let me just show you. So let me just pull this out. Okay, so from here you can see that text is rather large. So what we can do is plot the histogram of text. And you can see that the distribution is from 200 to 700. If we plot the similar distribution of, let's just say, the small number, cast we know is that it's a binary, is either 0 or 1. We can actually try Nox. And again, you can see that this is significantly smaller from 0.4 to 0.9. And obviously, text is going to drown out Nox. The other thing that we need to bear in mind is the actual distribution itself. So hence the reason why we, to perform point 2, which is the impact of the variable on the actual overall model itself, we need to actually standardize the variable. But before we do the actual standardization, what I will do is actually just run a basic linear model basically as our control, and let you have a look at what the coefficient of the individuals look like. We did this earlier, and you can see that Nox is really large, H is really small, as is B here. Now what happened when we actually standardize it? We're using scikit-learn pre-processing standard scalar, and also using the make pipeline, just so that we allow us to just tweak a little bit. In this case, just the scalar or standardize it. So the standard scalar, we instantiate it using and store it in this or instantiate and call it scalar. And from the make pipeline, we just provide scalar model. So here we have standard coefficient linear regression. Okay, and we'll run that, and we fit our model, and we are extracting. So we run the fitting of the model itself, and then we extract the coefficient, all right, and along with the column itself, and we actually sort in accordance to the significance of the coefficient, which is similar to what we did earlier here. So let's just print it out, and notice there's a distinct difference here. Notice Nox is no longer the top, okay, as it was here before. Well, we did mention that Nox is very small, so because of that, it actually magnified the coefficient. What you can see here in terms of the significance, L stat is actually the most significant, and H is the least significant here. So that's really one way that you can actually identify the key features, is by standardizing your variables, converting them to -3 to +3. Through that standardization, basically all of the values is now between the range of -3 and +3. That is really important, because from that you can tell, because they are now on the same scale, you can see which one actually explain the variability better than the rest. The next step, the other method that you can use, is to use R-square to identify key features. How do you do that? You compare the R-square of the model that you have against R-square of the model without a feature. So comparing have and have not, a significant change in R-square basically signify that the feature is really important. Okay, again we import R-square. We run the full model itself, which is everything being provided, and gives us the actual R-square of 0.74. Now, since we already identify L stat is the most significant coefficient, because after standardization, we'll run it without L stat. Notice that I dropped it off and see what happened to the R squared. Notice the R squared dropped quite significantly from 0.74 down to 0.68. Now, if we run the same without age, now remember age is the one that has the least in terms of contribution to the model itself. And let's see what happened to the R squared itself. Notice that, well, literally almost no change. And you can see now that age, as we have correctly identified from here, after you take it out from the actual model itself, basically R squared didn't change much at all. So from that exercise, you can tell that L stat is really important, whereas age is not really all that important as well at all in the model. Okay, so that's really the end of this exercise and this tutorial. What I'd like you to do is to actually get your hands dirty and try this out yourself. What I'd like you to do as an exercise, this should be quite a simple one, is to try drop off DIS, distance, and also RM, and see how does it actually individually contribute towards the R square itself. So this the exercise I'd like to leave you to try it out, and when you come back, I'll summarize the lesson. Welcome back. So how did you find that exercise? I hope that has been useful. It should be quite straightforward. Really, it's just dropping off a variable and recalculate that cell again to see, what the R squared change looks like. So in this lesson, in essence, what we've done is actually utilize the correlation matrix to identify collinearity between predictors. We mentioned that for the purpose of data science, it's not so important, in terms of the so-called collinearity does exist in the model itself. Ultimately, because they are self-contained in terms of it doesn't actually affect the prediction itself. So that's why we're not so concerned about the presence of collinearity. But it's good to know because for a start, you understand, where, which two variables or which three variables have collinearity problem. And also from a statistics background, it pays to actually pay attention to that as well, to see how it actually impact on your model. So that's the first thing that we did. Second thing that we did is that we also use eigenvectors as well as value to detect collinearity. And the third thing that we did is really identify which feature is the most important and which one is the least important. Couple of ways that we did it is via standardization of the variable itself. From standardization, we can tell that which variable is, which few variables are significant, which few are not significant. The other method too that we use to identify those features that are important is we use R square. Again, we just basically iteratively deduct or remove a feature and see how it impacts on the overall R square itself. I hope you find this lesson useful. What we are going to move into in the next video is basically try to implement an ordinary least square regression. Okay, but the difference this time is we are using gradient descent, a really powerful tool for estimation of our model. I look forward to seeing you in the next video.